Hello everyone. Here's the video where I'm going over all of the physics principles that we learn about and apply in Physics 20 and 30. There are a number of reasons why you need to be very familiar with these physics principles. The first overriding reason, and we've talked about this numerous times in class, the students who are going to be more successful in solving physics problems are the ones who don't just look for a formula from their formula sheet, because sometimes the formula isn't there. The students who are going to be more successful are the students who see the bigger picture and apply physics principles, because quite often those physics principles, the applications of them, lead us to a formula that's going to allow us to solve the problem. There happen to be 10 physics principles given on your formula sheet. The first 3 deal with forces, and then it gets into energy and momentum and more energy and mass energy and all of these other things that rounded out the course. Another reason why you need to be familiar with these 2 physics principles is, just like our unit exams, when you write your diploma exam, the final 2 questions on the diploma exam will be a pair of numerical response questions, one of which is a calculation question where you have to apply 2 physics principles in order to solve the problem. And those problems, as we've seen in class, can be quite complicated. So once again, if you don't see the bigger picture and you don't apply the physics principles, you probably don't have much of a chance of getting that first numerical response question in that pair correct. The second numerical response question following that is always going to ask you to list the 2 physics principles from your formula sheet that you used to answer that previous question, and you have to list them in the order in which they were used. So once again, being familiar with these physics principles will allow you to be more successful in general in solving problems, but then you also have that specific numerical response problem paired with the question that asks about the 2 physics principles used. I'm going to start off not by going through all of the physics principles, but I'm going to look at force to begin with. There are a number of different force analyses that we performed in this course. The first thing we're going to look at is balanced forces. And balanced forces refer to, on your formula sheet, what's called physics principle 0. Now, physics principle 0 has net force equal to 0, and that's really what the physics principle is. Yes, if F net is equal to 0, it's uniform motion. But the key idea here for physics principle 0 to be applied is that the forces are balanced. That means that although you may have 2 or 3 or more forces acting on some mass, they all balance. You have just as much force in each direction as you do in each opposite direction. And the result is that you have no acceleration. And that's what we call uniform motion. 0 acceleration means the velocity of the object is constant, so we refer to that as uniform motion, constant speed in a straight line. However, that does include masses that are stationary, and more often than not, in Physics 30, when we consider applying uniform motion, the phrase uniform motion can be a little misleading because we're dealing with objects that are stationary. A stationary mass is considered uniform motion because it is not accelerating. Its velocity is constant. So, we're dealing with balanced forces. If there are 2 forces that are balanced, then the net force is equal to 0. And those 2 forces must have equal magnitudes but opposite directions. So, for example, we can balance a gravitational force with a magnetic force. We can balance an electric force with a magnetic force. And we can balance a gravitational force with an electric force. Gravitational forces, magnetic forces, and electric forces are the 3 forces we learn about in high school physics, at least in terms of calculating their values. If a gravitational force is equal to a magnetic force, an example of that would be where you have a current-carrying wire in a magnetic field, and it is experiencing a magnetic force away from the surface of the Earth due to the relative directions of the current and the magnetic field. And as a result, you've got just the right amount of magnetic force. You've increased the current or decreased the current to that sweet spot where the force on the wire upwards is equal in magnitude to the force on the wire downward. If an electric force is equal to a magnetic force, we've seen a situation like this with Thomson's charge to mass ratio experiment. In the first part of his experiment, a beam of cathode rays, which we now know are electrons, is undeflected as it passes through a perpendicular electric and magnetic field pair. And as a result, the magnitudes of those two forces are equal and their directions are opposite. And that's what accounts for the undeflected beam. Or we can have a gravitational force being balanced by an electric force. The classic example here would be Millikan's oil drop experiment. Notice, by the way, with Millikan's oil drop experiment, I'm saying that the oil drop, which is being forced upward because of an electric force and downward because of a gravitational force, that oil drop might be moving with a constant velocity, or it might be stationary. Of course, with any of those, if you need to calculate the force due to gravity, you're probably going to use Fg equals mg. If you're going to calculate the electric force, most likely you're going to be calculating it using the electric force is equal to the charge times the electric field strength. And you may have to determine the electric field strength by taking the voltage between plates divided by the distance. And then, of course, if you have a magnetic force, it depends on the nature of what is being forced. If it's a current-carrying wire, you're going to use Fm equals ILB. And if it's a single charge or a charge in a beam of particles, you're going to use QVB. There's another situation. We're going to stick with balanced forces here. There's another situation where we can apply balanced forces, or the concept of F net equals 0, which is still physics principle 0 on your formula sheet. And that's if you have three forces competing against each other in 2 dimensions, and yet the object is stationary. That means that all of the forces add up to 0. A classic example here is when you have a pith ball suspended on a thread and it is attracted to some other charged object. So there's an electric force pulling this pith ball to the right in the diagram because maybe there's a Van de Graaff generator which is attracting it on the right-hand side. Or maybe there's a charged object on the left-hand side of the screen which is repelling that pith ball. But the electric force is to the right. The pith ball has mass, so there's a gravitational force down. And there has to be a third force, because if there were not, then that pith ball would take off in the general direction of those two forces. And that third force is the force of what we call tension, which is the force that the string is pulling on the pith ball with. And because the pith ball is stationary, and we saw this in a demo in some of the lab work that we've done in class, it just hangs there at an angle, and that angle can be measured. But because it's stationary, all three of these forces have to add to give 0. Now, what you're looking at here is called a free body diagram. In order to analyze this situation, you have to create a vector diagram. And a vector diagram involves taking those three forces and drawing them tip to tail. So we have the force of tension pulling up and to the left. We have the force of gravity pulling the pith ball down, and I'm drawing it tip to tail. And then the third one, tip to tail, is the electric force. And what's important is these three vectors add up to give 0. When I start drawing the tension force, I end up finishing my vector diagram at exactly that place where I started drawing it. Of course, we know that angle. So how is it that you analyze things here? You don't analyze things with a formula in general. You analyze things by using trigonometry. Usually you're asked to find the electric force, but not always, and we'll talk about the other situation in just a second. But basically what you can do with this triangle is you can write out what tangent of theta is equal to. It's equal to the opposite side, which is the electric force, over the adjacent side, which is the force due to gravity. And now you have a formula relating the angle of deflection of the pith ball with the electric and gravitational forces. The sine of the angle is opposite over hypotenuse, so that would be the electric force over the tension force. And the cosine is equal to adjacent over hypotenuse, so that would be the force of gravity over the force of tension. Of course, the force of gravity is the one thing that you can calculate as long as you know the mass. So there are a number of ways this can be presented to you, but one of them is you're told the mass and the angle, and you're asked to find the electric force. Well, if you know the mass, you can calculate the gravitational force. If you know the gravitational force and the angle, then it's pretty easy to use this relationship here to find the electric force. On the other hand, maybe you're asked to determine the tension in the string. Well, what I would recommend is calculating the electric force first if you know the mass, and then you will know the electric and gravitational forces, and then when you take a look at this triangle, you can calculate the tension force by using the Pythagorean theorem. There are a number of different ways that you can approach this problem. Looking at it again right now, I realize that if you use the cosine with the angle, you could find the tension force with the mass that you're given. But the bottom line is you're solving this kind of problem with a trigonometric approach, not a physics approach directly. The physics is the diagram. You're not really using physics formulas. This idea can be extended as well to a current carrying wire that's suspended in a magnetic field. We saw a demo that I used numerous times in class. It wasn't a wire, it was a U-shaped swing that was suspended at an angle, but the principle was the same. For example, and this is a diagram I often see on diploma exams, we've got a horseshoe magnet, and you can't really tell, but that suspended conducting rod is hanging by very thin wire, and it can swing kind of into the page and out of the page. And here's a side view. So you're told maybe that the angle of deflection of that wire, and all you're seeing in the diagram on the side view is the end of that wire, the end of that solid conducting material. Maybe you're told that it's deflected at 21.5 degrees, and you're told the mass is 42 grams. What can you determine from that? Well, you can determine the magnetic force, because what we've got are three forces acting on this conductor. Let me just fade things out a little bit for you here. The tension is in the direction of the wire that's suspending that solid conductor. The magnetic force is to the right side of the page in that diagram. The force of gravity is down. So again, what you can do is you can draw these three tip to tail, and then knowing the mass, you can find the force due to gravity. Then you can use the angle that's given along with the force of gravity to find the magnetic force. There's another layer, though, to this compared to the hanging pith ball, and that's that the magnetic force on the current carrying conductor is ILB, so maybe you can take it further and use the magnetic force you found from the angle and calculate the magnetic field strength, because you look at the ammeter and you can read the current, and you measure the length of the wire in the magnetic field. That pretty much sums up all of the situations that I think you might encounter or you could encounter dealing with physics principle 0. Physics principle 1, I call unbalanced forces causing a linear or an instantaneous acceleration. I do want to talk about this in a little more detail, because I think the way these physics principles are described between 0, 1, and 2 can be a little deceiving. So first of all, this is the physics principle we're going to be working with for the next few minutes, accelerated motion. And I have a bit of an issue with that. I always have had an issue with them saying that's accelerated motion. It is, that's true, but I'm going to refer to it as what's called linear acceleration or instantaneous acceleration. And the reason for that is Number 2 is also accelerated motion. It drives me nuts that they call number 1 accelerated motion, but they don't elevate number 2 to the status it deserves, which is also accelerated motion. They're both accelerated motion. The difference is when you use physics principle 1, typically speaking, you're ending up using F net equals ma to calculate a linear acceleration in meters per second squared. However, when you use physics principle 2, you're typically using F net equals ma, and then you're changing the acceleration to v squared over r because it's circular or centripetal acceleration. And you're still getting an acceleration in meters per second squared, but it's towards the center of the orbit of whatever is accelerating. So they're decidedly different. I'm going to refer to this as centripetal accelerated motion. I think that's the best thing that you can call what we're talking about in physics principle number 2. So this is what we're dealing with though, right now, is accelerated motion that's linear or what's called instantaneous. Linear means you're speeding up or slowing down in a straight line. I'm going to get to instantaneous in a minute or two. So what are the situations we can encounter where there's an instantaneous acceleration or a linear acceleration? Well, basically, if there's a single force acting on that object, that single force is the net force, and it's going to cause an acceleration. And provided that force is either in the same direction as the original motion or in the opposite direction, that's what we call linear acceleration. So for example, if I put a charged object in an electric field, or I put it next to another charged object, in either of those cases, no matter how we think about it, there's an electric force on the charge, so there's an acceleration. And the idea here is the electric force and the net force are the same force. So you can go to your formula sheet, and for Fe, you can put in, well, QE, and for F net, you can put in MA. So just toggling back to this page for a second, when we have Fe equals F net, all we're saying is the electric force and the net force are the same. So I can take the mass times the acceleration, which is the net force, and set it equal to the charge times the electric field, which is the electric force. And by the way, you may have to use voltage over distance to find the electric field. The electric field in these formulas on the right are capital E's. Maybe it's something as simple as you have two charged objects and one is released. What's the acceleration of the one that's released? If that's the case, then you're going to use Coulomb's law instead of F equals QE. Millikan's oil drop experiment is a perfect example of linear acceleration or application of it, but not the situation where the drop is suspended. If the drop is suspended, then we're talking about physics principle 0. And right now, we're focusing on physics principle 1, linear acceleration. So perhaps in an oil drop experiment, we have those two forces that you're looking at right now acting on that oil drop. Well, if the electric force is greater than the force of gravity, the drop accelerates upwards towards the sky, towards the top of the screen. And if I said to you, what do you do to those two forces to find the net force? It's technically wrong to say you're going to subtract the two forces. You're going to subtract the two magnitudes of the forces. So by putting magnitudes in that equation at the bottom, and by me subtracting the magnitudes, I don't have to include negatives anywhere in any of my calculations. It's already done. And that's a case where the object is accelerating up in Millikan's experiment. Now, the drop could be accelerating down, but it could be accelerating down because there is still an electric force up, but it's smaller than the force due to gravity down. However, it could be accelerating down because both forces are down. So it could be accelerating down because one force is up and one force is down, but the downward force, which is gravity, is just a bigger force. or it might be accelerating down if both forces are down. You can recognize which is which by looking in the question at the magnitude of the acceleration. If you're told the drop accelerates down at 3 meters per second squared, well, that's less than it would be accelerating down due to gravity, so electrical forces must be taking something away from the influence of gravity. Whereas if I tell you it's accelerating down at 15 meters per second squared, that means that both forces have to be down because 15 meters per second squared is more than gravity would supply, which is 9.81. In the middle situation on the screen, the net force can be equated to the magnitude of the force of gravity minus the magnitude of the electric force. In the first two of these situations you're looking at, we're basically saying when you have forces that are in opposite directions, the net force is the difference between them, and you take the bigger magnitude minus the smaller. In the third situation, since both forces are in the same direction, the net force will have a magnitude that's equal to the sum of the magnitudes. And again, you know, what's at the bottom of the screen here, you have to know enough that you would, any place you see an F net, you would put MA, because that's how you calculate F net. Any place you see an FG, you would put MG. We've talked about this a lot. There's a difference between A and G. A is the acceleration that the drop is actually experiencing. G is the gravitational field strength near the surface of the Earth, which is 9.81 newtons per kilogram. Any place you see an electric force in those Millikan equations, then you're going to use this formula, take the charge times the magnitude of the electric field to get the electric force. You may have to take the voltage between the plates divided by the distance between the plates in order to calculate the electric field strength. Again, and I'm mentioning this because the electric field strength formula that's highlighted here, electric field strength equals electric force over charge, it doesn't have absolute value signs in it, but in all of these situations, we use absolute values. We've included or incorporated the negatives in by subtracting magnitudes. We could have a moving charge acted on by an electric field and a magnetic field. And in Thomson's charge-to-mass ratio experiment, we learned that if those two fields are perpendicular, it's possible for the moving charge to not be deflected. However, we're talking here about the charge being deflected. When we talked about physics principle 0, we said, oh, Fe can equal Fm in Thomson's experiment. Here, they're not equal because the charge is deflected. So we're talking now about physics principle 1, but it's not linear acceleration. It's called what I call instantaneous acceleration, because as soon as that pair of forces, the electric force and the magnetic force, act on the particle, it's going to change direction. And we know something about magnetic forces. The direction of a magnetic force depends on the direction of the motion. And what's going to happen is the magnitude of the net force is going to immediately change because the direction will change. And because of that, the object is not going to travel in a straight line. It's going to be traveling in some kind of a curve. It will not be circular because there's also an electric force. It will be traveling in some nonlinear fashion, so I refer to it as instantaneous acceleration. So getting back to this situation, it could be that the electric and magnetic forces produced by those two perpendicular fields are in opposite directions, but the charge is deflected in the direction of the electric force. Think about that for a second. What that means is the electric force must be greater in magnitude than the magnetic force because they're in opposite directions and the electric force wins. That means the magnitude of the net force is found by taking the magnitude of the electric minus the magnitude of the magnetic force. It could be that the two forces caused by those perpendicular fields, that those two forces are in opposite directions, but the magnetic force wins because the particle is deflected in that direction. In which case the net force is going to be found by taking the magnitude of the magnetic minus the magnitude of the electric. Remember, when you have two opposite forces, the net force is found by taking the magnitude of the bigger minus the magnitude of the smaller. And the third case is it could be that the electric and magnetic forces end up being in the same direction due to the relative orientation of the two perpendicular fields, in which case the net force would be equal to the sum of the magnitudes of the forces. Again, F net can be found using MA. Fm can be found using QVB. I've never really seen a situation where what we're talking about right now would apply to F equals ILB. And the electric force can be found by taking the charge times the electric field. Of course, again, the electric field can be found typically by taking voltage between the plates divided by distance between the plates, if it's that situation. You may just be told the electric field. We're moving on now to physics principle 2, which is where we have an unbalanced net force causing circular centripetal motion, also known as, on your formula sheet, uniform circular motion, which I don't think says enough. I think, when you see uniform circular motion on your formula sheet, you should know it means more than that. There's an unbalanced net force, which means there's an acceleration. It's just that the acceleration is towards the center of a circular path. So this is what we're talking about right now. If the net force causes centripetal acceleration or motion, then the force causing the acceleration is set equal to the mass times the centripetal acceleration. I'll be very clear here. The first situation I have is F net equals Fe. This would be applied if you had a problem where you were told in a hydrogen atom an electron is moving in a circular path with a certain radius. We could apply this situation. I want you to notice that I'm not saying magnitudes of these forces are the same. And this is a subtle thing, but it's very important here. When I say F net equals Fe, not just the magnitudes, the forces, that's because they're the same force. It isn't that there's a net force and there's also some other force called an electric force. The electric force acting on that electron in orbit in hydrogen, that electric force is the only force acting on it. So it's the net force. What you would do is you would say, well, Ma equals that force. Ma is how you calculate the net force always. And in this particular case of an electron in orbit around a positive nucleus, you can use Coulomb's law to write out how to calculate the electric force. That C is important. It is a net force, which is Ma, but it's a special type of acceleration, which is called centripetal. And centripetal acceleration can be found by taking v squared over r. So the formula I have at the bottom of the page is what you would end up creating for this situation. By the way, that's a perfect example of, I don't think anybody's going to memorize that. I don't think anybody's going to get to a diploma exam, see a question talking about an electron in orbit around an atom and say, oh yeah, that's that formula mv squared over r equals kqq over r squared. I just don't think most people's brains work that way. But if you understand the physics principles, you can build it. Second situation, well, it could be the net force that's causing centripetal motion is caused by magnetism. It's a magnetic force. And by the way, anytime you have centripetal acceleration, the direction of the force is perpendicular to the direction of the motion. And this is always the case when you have a charged particle moving in a perpendicular magnetic field, because your right-hand rule will predict that direction. This time we're going to say ma, which is net force, equals qvb. The acceleration, of course, is centripetal, so we develop this mv squared over r equals qvb. So we can apply this F net equal to Fm, or we can apply F net equal to Fe. Can we apply F net equal to Fg? Certainly, except that you did this in Physics 20. I don't see any reason why you would have to do what I'm about to show you on a diploma exam, but I'm including it here for completeness sake. You would say ma equals gmm over r squared, and hopefully you remember doing this in Physics 20. This becomes mv squared over r equals gmm over r squared. One final note about this: the reason we're changing ma to mv squared over r is because a is v squared over r. However, and this is the final note, a is also equal to 4 pi squared r over t squared. So if you are given a question that asks you to find the period instead of the speed, you can substitute in 4 pi squared r over t squared. Or, if you were like me, if you were asked for the period, I wouldn't do that. What I would do is I would find the v using v squared over r, and then I would take that v and set it equal to 2 pi r over t to find the period. All right, various other force analyses, not other, pardon me. Part B of this handout says various force analyses based on the descriptions of the scenarios. Everything in the last half hour I have been explaining starts with the force analysis and gives you scenarios that match it. In your handout, Part B is just turned around. All that happens in Part B in the handout, which I'm not going to go through, is I start listing every single scenario that we've come across in this course, and I tie it back to the physics principles. C, various applications of conservation of energy. This is very important. Physics principle number 5. The photoelectric effect. The purpose of this video and this handout is not for me to review all of the concepts, so I'm not going to go over in detail the photoelectric effect here. But you should know that in the photoelectric effect, a photon is absorbed by an electron, and the electron, if it's given enough energy, is ejected from the metal. Well, how do you find the kinetic energy the electron has once it's outside of the metal? You take the photon energy that was given to the electron, which is the energy the photon had before it was absorbed, and you subtract what's called the work function. This is using the law of conservation of energy. Whenever you're dealing with electron transitions in atoms, where you have an energy level diagram and you have an atom that makes a transition, the change in energy of the electron in the atom, which is always the upper energy level minus the lower energy level, will be equal to the energy of the photon. This is conservation of energy. The photon is absorbed if the electron moves to a higher level, and if the electron moves to a lower level, the photon is emitted. But in either case, the energy of the photon is equal to the change in the energy of the electron, and you always use upper minus lower. This is conservation of energy. The Compton effect. Well, the Compton effect happens to include conservation of energy and conservation of momentum, but we're talking about energy right now. Again, my job in this video is not to review everything about the Compton effect. There's formulas involved, there's other nuances to these problems, but in the Compton effect, much like the photoelectric effect, a photon strikes an electron. The difference is in the Compton effect, the photon strikes an electron that's free, and the photon is not absorbed, it's scattered. So before the collision, you have a free electron which is at rest, and you also have a photon with energy. After the collision, you have a photon that has less energy than the photon had to begin with, and the electron has kinetic energy. And this is essentially what you do to solve those problems. The incident photon energy equals the scattered photon energy plus the kinetic energy of the electron. And by the way, these two energies are both calculated using E equals hc over lambda most of the time, although I suppose they could each be calculated using E equals hf if you were given the frequency before and after. This energy is found using 1/2 mv squared. Again, it's conservation of energy. Alpha particle scattering, where you have an alpha particle that's quite far away from a nucleus, and as the alpha particle approaches a gold nucleus, it slows down. And we're talking here about deflections where the alpha particle is deflected back 180 degrees. Essentially what we're talking about here is the alpha particle, when it's quite far away from the nucleus, has all of its mechanical energy in the form that we call kinetic energy, 1/2 mv squared. When the alpha particle gets closer and closer and closer to the nucleus, and again, this is only going to happen if it's deflected with 180 degrees, the alpha particle slows down, losing its kinetic energy, but more importantly, at the point of closest approach, it stops momentarily. And it's at that point in time that all of its mechanical energy is now potential. And essentially the kinetic energy at the place where I have VI in the diagram and the potential energy at the place where I have VF, those two energies are equal. Now this KQ1, Q2 over R is potential energy. It's not a force. It's not Coulomb's law. And the formula for that potential energy, EP equals KQ over R, would be given to you in the context of a question. In this application, by the way, Q1 would be the charge of an alpha particle, which you should know, 2 elementary charges. Q2 is the charge of a gold nucleus, and you would look at your periodic table and see that gold is number 79, and you would take 79 times the elementary charge to get that charge. X-ray production is another example of conservation of energy. During X-ray production, and we learned this on the very first day of Unit 3, when I went through how all of these forms of EMR are produced. X-rays are produced by high-speed electrons suddenly being stopped by a metal target. And what happens is all of the energy that each electron possesses when it stops, all of that kinetic energy is lost in an instant, and it's produced or accounted for by the production of a single photon. And the electron energy and the photon energy are equal. So, I mean, how can you calculate the electron energy? You could calculate it using 1/2 mv squared. You could calculate it using the charge times the accelerating voltage, because voltage is energy over charge. How do we find the photon energy? Well, you could use E equals hf or E equals hc over lambda. Regardless, when you set either of these formulas on the left equal to either of the ones on the right, you're using conservation of energy. So we've covered all of the applications of force. We've covered all of the scenarios that involve conservation of energy. And now I'm going to run through all of the other physics principles. So, conservation of momentum. Obviously, it means that momentum before is equal to momentum after. When can you apply this? You can only apply momentum before equals momentum after if the collision between the objects occurs in an isolated system, which means that during the collision, there are no outside forces present. Sometimes, and I don't care for how this is worded, but sometimes on a diploma exam it says during the collision, no significant forces of friction are acting. Bottom line is, during such a collision, you can set the total momentum before equal to the total momentum after. Listen though, if it's a linear collision, you are allowed to write mv plus mv equals mv plus mv. If it's linear, then you just put positives on velocities that are to the right and negatives on velocities that are to the left. However, if it's two-dimensional, you have a different road ahead of you. You have to look at a vector diagram and solve it using a higher level of trigonometry. Or you have to look at finding all of the components of all of the vectors before and after and using total x momentum before equals total x after, and do the same thing with y and proceed down that road. Conservation of mass energy, this is an important one. Basically, in nuclear changes, in all nuclear changes, fission, fusion, artificial transmutation, alpha decay, beta decay, positron decay, gamma decay, electron capture, during any nuclear change, the mass of the system will change. And again, we've talked numerous times about this in class. I'm not saying that the mass is just somewhere else. The mass either decreases or it increases. You actually lose mass. You still have the same particles floating around. They are just collectively less massive or more massive. That change in the mass is equated to the change in energy by delta E equals mc squared. The one example I didn't give in my list, and it just occurred to me, is when you talk about binding energy and mass defect. When you tear apart a nucleus, if it's possible for you to tear apart a nucleus, the mass will go up. And that change in mass, which is called the mass defect, is delta M, and the energy needed for it to happen is called delta E. That's the energy you put in, and you use delta E equals delta mc squared. Listen, it doesn't matter what type of change it is, but if the mass decreases, then energy is released, and that's exothermic. And we've talked about this numerous times as well. If you're in Chem 30 and have taken Chem 30, you understand this concept of naturally occurring processes being exothermic, maybe at another level because you've already applied it to chemical changes. But natural processes that are nuclear would be fission, fusion, any radioactive decay, any nuclear process that occurs naturally, electron capture, for example. If the mass increases, then that means energy must be added to the system, and that means it must be an exothermic change. During artificial transmutation, that may be what happens. I have seen examples of artificial transmutation where it is exothermic, but the only place it can be endothermic is artificial transmutation. This physics principle is basically used whenever mass, that should say, whenever mass is converted to energy. So matter-antimatter annihilation. Or when matter is created, for example, using pair production. Conservation of charge, this is physics principle 7. When do you use this? Well, when you touch two similar objects together that are both charged, or one of them is charged, without grounding any of them, and we say that the total charge is shared equally among both objects, that's conservation of charge. You know, a classic question is where you have a charge on one object of positive 8 microcoulombs, and you have a similarly shaped object with the same type of material, and it's negative 3 microcoulombs, and they are touched together and then separated. What will their charges be after they are touched and separated? Well, when they're touched together, what we have is a total of 5, positive 5 microcoulombs. So the law of conservation of charge says we must have a total of 5 microcoulombs afterwards. And if they're similarly shaped and they're similar sizes, then that charge will be shared equally. And then you might have to do a Coulomb's law calculation combined with F equals ma, who knows. But the bottom line is the total charge before, positive 8 and negative 3, and the total charge after, positive 2.5 and positive 2.5, are the same. It's also used to explain electrostatic interactions in terms of charging by friction, charging by conduction, charging by induction. It's used to explain what's happening when you ground objects, when lightning strikes occur. All of those things involving electrostatics are all happening because charge is conserved. Conservation of charge is also used to predict atomic numbers that are missing in a nuclear equation. For example, if I have the fission of uranium-235, I hit the uranium-235 with a slow-moving neutron. I get two main fragments. This is what makes it fission. I get krypton-92. I get some other element, which is unknown to me. The X there means I don't know it. Its atomic mass number is 140, and I get a certain number of neutrons. And I say to you, what is the value of Y? Well, the bottom number in any nuclear equation is charge. I know that you know the bottom number is also, most of the time, protons, but not always. However, the bottom number is always charge. You use the law of conservation of charge to find missing numbers on the bottom. So on the left-hand side, I have 92 in total, highlighted in blue. On the right-hand side, neutrons have no charge. Krypton has an atomic number of 36, which means it has a charge of positive 36, because that means 36 protons. And that means I have to take 92 minus 36 and get what I believe is 56 for the number of protons in that missing element, which means that charge is 56. But I'm using, even though I'm thinking about protons here, I'm using conservation of charge. Conservation of nucleons, well, that's only really used in one place, and that's to predict the atomic mass number. That's the top number, not the bottom number. The atomic mass number during a nuclear change. So looking at this same situation, we've already determined that the bottom number for Y is 56, and we could certainly look up what 56 is on the periodic table. I think it's barium, but I don't know. That's not relevant, though, to finding out what B is in this equation. If I said to you, what is the value of B? Well, we have to look at the top numbers. On the left-hand side, we have 235 plus 1, which means we have 236 nucleons. And that means we have to still have 236 nucleons after this change happens. And what do I have on this side? Well, let's take a look. I have on the other side, I have 140 plus 92. 140 plus 92 gives me 232 nucleons. And according to my math, if I have 236, then I need another 4, because I had 236 in total. And that means that I need a total number on the top of 4, and that means that B must be 4. But what I used is the law of conservation of nucleons there. Don't assume, because you've seen a fission reaction, by the way, that this number that is 4 should be 3 or 2. Every fission reaction is different. It's not about memorizing things. It's about, to go all the way back to the beginning of this, it's about applying physics principles. And the last physics principle, well, not really the last, there's one more I want to talk very briefly about. The last physics principle is wave-particle duality. Anytime we're talking about the de Broglie wavelength of electrons, or diffraction and interference of electrons, or even, in the Compton effect, when we calculate the momentum of a photon, these are ideas that are, as I say in class, there are two sides of the wave-particle duality coin. The one side, which is a de Broglie wavelength, says that particles with mass can behave like waves. The other side, which is the Compton momentum idea side, says that photons, even though they don't have mass, have momentum. And what I would say to you is anytime you use this formula P equals h over lambda, or maybe you turn it around on its head and you write lambda equals h over P, and then you change that to lambda equals h over mv. Anytime you use any variation of that formula, you're applying the principle of wave-particle duality. Now, I do have one more physics principle that's on your formula sheet, and we didn't address it. It's the work-energy theorem. But as I've said in class, and I'm just going to remind you, I would steer clear of the work-energy theorem. Basically, you can use the work-energy theorem, this is the way I see it. You use the work-energy theorem, which is force times displacement equals change in energy. You can use that if you know the force and the distance. However, to do some of these complicated multi-principle physics problems that require use of conservation of energy, that will always work, whereas the work-energy theorem doesn't always work. It's a little complicated. What I'm saying is anything you can do with the work-energy theorem, you can do with conservation of energy. However, not everything with conservation of energy can be done with the work-energy theorem. So I would just say to you, don't use the work-energy theorem. That's the bottom line. I hope that that helps you out for your diploma exam. Again, this is not about content. You're going to have to go back and rewatch those videos on all of the different units and all of the different topics, and you're going to continue to have to practice physics questions between now and when you write your diploma exam. In the meantime, I hope to talk to you all soon. Take care of yourselves.